traveling salesman problem. We have a set of cities: Albuquerque, Buffalo, California. I know. What? Chicago. We have a set of cities A, B, C, D, and E. We have some set of distances between them, and our aim as an optimization problem is to find, say, some tour that goes to all 5 cities and returns to the starting city, such that when we sum the values on the edges, it's minimized. For you computer science people, if you make this into a decision problem, it's NP complete. Okay. So we discussed this idea of universal Darwinism. So we discussed doing mutation and crossover, and we discussed, we broke up into groups, and we discussed how things might evolve. And you can imagine doing a genetic algorithm and having something like evolution, but at least what makes a GA? A GA is some notion of selection, which we can keep the same, but somehow we're going to need mutation and crossover. With a little bit of thought, you can kind of see that we can't exactly do mutation like we did on a bit string. We can't exactly do crossover like we did on a bit string. So some things go wrong. But we wanted to choose operators that have the same principles, i.e. mutation should still be some form of local search. We don't want to make a big change, whereas crossover is potentially a much larger change. It takes 2 individuals, and we hope to combine information between them, and so you may have quite a big change if the individuals are quite different. But somehow if the individuals are very similar, we expect the crossover operator to change them very little, since there's not much difference between them already. Okay? So we want to find analogs for these operators in the permutation as opposed to bit strings. Okay? And when we go to genetic programs, we'll want to do the same thing for code. We'll want to think about, well, how do you mutate a piece of code, and how maybe could you cross over a piece of computer code. Okay. So many problems other than the traveling salesman problem can be expressed as a permutation problem, but traveling salesman problem is going to be the one that we're particularly interested in. Okay. Exponential in the size of the number of cities, i.e. and factorial. It gets hard fast. You can't enumerate all possible solutions. You can't use random search with any sort of hope in doing well. But if you want to try in your code random versus your TSP, you can see how it performs to give you a feeling if you're doing anything better than random. This is something you should always think about when you're running your genetic algorithm. You're testing, you want to see how well it does. Well, maybe you should think about what are the baselines you compare your GA to. Well, maybe you want to have something that's just generating random solutions. If you're not doing better than random, and there actually is some structure to your space, well, there's probably something wrong with the details of your GA here. Likewise, it's not going to happen for every problem, but maybe you want to have some simple discrete hill climbing approach where you always have a single point in space, and you're always trying to go to the closest nearest point, and then you get your solution after you can no longer climb anymore. Maybe you randomly restart again. Another simple discrete optimization algorithm. These are kind of interesting baseline comparisons to see if your evolutionary algorithm is doing anything for you. Okay, TSP. You can imagine that I have some tour here. My tour is, I go to city A, then I go to city C, and then I go to city D, I go to city B, I go to city E, and then I return to A. Now, something's going to go wrong for mutation. Well, obviously I don't have bits, but maybe think, oh, I'll just put in a new random letter. So I'll go, oh yes, I'll mutate D. What size should I choose? I choose C. But oh, damn it, it's not going to work. So we need to come up with something else. That we want somehow to be a local change to our solution, not a huge change. Well, why save it for you? The one which there's other possibilities, but the one I'm going to ask you to certainly implement in your coursework is you choose 2 locations at random and you simply swap. Okay? We'll look at a pictorial representation of that in a moment, because pictorially it's kind of neat. Okay. Another operator. Insertion, kind of similar. We choose 2 points, and what we do is we bring this over here and push everything to the right. Swap is as I said. Where are my notes? Imagine we have a traveling sales tour called Euclidean tour on a plane, i.e. maybe we have a tour between different points and the distances correspond to the Euclidean distance between these points. So maybe it is like actually going around England. And our tour looks like this. Any obvious change that you could do to improve it? Can you see this? I like a challenge. You have to think what I was doing. Okay, let's draw it here. So we have a tour that maybe looks like this. Here to here to here to here to here. And its actual distances in Euclidean space, without me pulling out a ruler, what could I do to improve that tour? Yeah, you swap, because you actually know that you can sit there, use the triangle inequality, take a moment to prove to yourself that if you ever have lines crossing on a tour in Euclidean space, that it's not the smallest possible tour given those points. Fun little geometric question for you to prove with the triangle inequality. And in fact, that does correspond to a swap. Okay. Slightly bigger sort of, arguably, mutation. Well, maybe not. Now, this is good as this is good, but maybe 5, you just kind of take this part of the tour, reverse it, and so now that 5 is connected in 1, and 2 is connected to 6. A more aggressive sort of mutation. Choose some subset size and randomly rearrange in that subset size. Same sort of, or a kind of problem just like, with our bit strings, we had no problem crossing over, but clearly if we just grab a single location and try to cross over, we'll have some problem. So we need some specialized crossover operators to, the hope is you have 2 different good tours and maybe you can combine good partial tours from 2 different areas. Okay. some of these are quite confusing. Hopefully I'll get them right, but you may have to, I have printed you a copy of the notes, because I often confuse myself. Let's I like to go from the pictures. Order crossover. And of course, this didn't quite print right. Let's check the notes. Okay, so how does order crossover work? Let's maybe I'll write it in. So here's our two candidate solutions, our two potential tours in our population. We've done selection, we've done mutation, and now we're going to cross them over to create two child candidate solutions or tours. So we grab the genetic information from 1, 4, 5, 6, 7, and then we try to fill in from the next. Okay, so well, starting here, we don't already have a 1 in our location, so we can grab the 1 and put in the 1. So we now have a 1 in there. What's the next one? There's a 4, but we can't grab the 4 because it would be duplicating. So we go to the next one, and we can grab the 9. Okay. We can go to the next one. We haven't used the 3 already, so we can put in the 3. We've used the 7, so we can't put in the 7. We haven't used the 8, so we can put in the 8. We haven't used the 2, and somehow I managed to do this right, probably because it's the easiest one. The other ones I will manage to confuse. This is the way order crossover works, and then we can do the exact same operation for the next thing. I'm going to ask you can certainly try other operators for crossover. Edge crossover is another good one to try for the TSP problem. Maybe slightly more difficult to implement, but please implement this.
No, sorry, quick question. In the problem, are you allowed to go back to cities we already visited or not? Is that
no?
Not,
In the traveling salesman problem, you only.
That's what I thought. Although something you said earlier made me think that otherwise. So the path length is equal to the number of cities, essentially.
Well,
plus the return.
It's a tour, so yes. So there's going to be, so if you have n cities, there's going to be n plus 1 distances, which you sum up. Or did I do that wrong? No. There's n cities, there are n distances.
Yeah.
That includes the return. Questions? Okay. Partially mapped crossover. I'm not going to read these bullets to you because it'll be informative, but we'll try to do this pictorially. You may have to read it carefully because I will potentially make a mistake here, but I will do my darndest to try to explain how this works. Helpful arrows and printed correctly. Okay, so same idea. Just like a 2-point crossover on a bit string, we grab two things and we use it, and the idea is we want to then fill in with the remaining genetic material. We have a difference in the bit string since it's a permutation, we can't repeat things, so we want to use as much information as possible. And hopefully I will get this right, but it's quite mind-bending. 4, 5, 6, 7. Okay, so now I want to start filling in information. So I look at so I have my 4, 5, 6, 7. Now the first thing I observe is that I want to get this information. I've already used the 4. So if I've already used the 4, what does that mean? What happens? How does this work? Is it, maybe I should read it.
Well, doesn't it just take the 4 and swaps it with the, kind of looks at what's the other number in the place and swaps it then with the 4 in the second? Looks at the 8 and then places the 8 where the 4 was in the second term, right?
Sounds right. So choose a random segment copied from P1. Starting from the first crossover point, look for elements of the segment P2 that have not been copied. So as you said, thank you, 8 hasn't been copied. Okay, I'll do that. So 8 hasn't been copied. I look, I go, well, if I had copied it, go where the 4 is, but where the 4 is in the new place, is where the 8 will go, because that's where the 4 was. Okay, so I get my 8 that way, and I also look and I see another one that's been used is the 2. The first step is hard, the second is worse. So I go, oh look, the 2 is where the 5 was, but so I'll try to put it where the 5 would be, but the 7 is where the 5 was. So I'll look at where the 7 is, and so the 7 is over here, and so I put the 2 there. And you know, I play a little ping pong back and forth until I eventually get it. And don't ask me for a formal proof of correctness, because no matter how many times I try to explain this, I immediately forget it. Because it's too complicated for me. But it's fine. I see it. Okay, then our life is easy, because those are all the conflicts, and we can start filling in an order. So we continue on. The next thing in order is the 1. We haven't used the 1. We've done all the things that we've used. It's a 1. So we put in the 1. We use the 4, so we ignore it. We haven't used the 9, so we put in the 9. We haven't used the 3, so we put in the 3, and we're done. Okay, it's the initial ping-ponging that you have to get. So the property of P, what does P-max accomplish by this complex ping-pong? It keeps as many things in their absolute. It tries to maintain absolute positions and order. So, for instance, once we swap the material over, for instance, in the 4, 5, 6, 7, we maintain the 9, 3, 7 in order.
One question. Is there actually a specific way?
I didn't want you to ask the questions. Did I say ask questions? One exception, when I come to this operator, I never want you to ask any questions.
It's about the first step. So,
okay.
Is there a specific way how I would actually choose the sequence that I would swap, like the 4, 5, 6, 7, and not kind of a different sequence?
No, it's forced. There's only one way you can do it.
No, I mean the step 1, like.
This.
Yeah.
No, you choose 2 locations at random.
Okay.
So in this thing, you sample a number from 1 through 9, then you sample a second number from the remaining numbers, and that gives you your segment to grab.
But there wouldn't be kind of a way that would look kind of whether these distances are short or anything like that, or whether this seems to be a good order.
Well, one change you can make to every GA, which may be benefit, is for a lot of these things like crossing over, swapping, is sometimes people look and say, well, I'll only do this operator if it improves the solution, or I'll only do this operator and I'll let myself not improve the solution with some probability. So sometimes people don't like to trust the randomness. Maybe it's not good to trust randomness in your setup, and you actually look to see if it improves, but you still, because you're hoping you're getting enough moving around from the mutation and the crossover. I don't know if that's the sort of answer you're looking for. But yes, PMX. Cyclocrossover. You know, I love explaining these operators to you, actually. I was kidding. I can't wait to explain cyclocrossover to you. But unfortunately, it's so useless for the GA. You know, it doesn't conserve the right things. I'm actually not going to explain cyclocrossover. Read it in your notes. It's actually quite bad for the TSP. Nobody has any good luck with cycles. So it's not appropriate because I can't remember what it maintains, but it doesn't maintain the useful wordings. Edge recombination, once more some complexity, but I'll attempt to explain how edge recombination works, and I encourage you to try it if desired, but it's not one of the required ones. Yes?
For these combinations, are there only one child in this?
No, you can do the opposite with the other parent. But once more, this is a tunable thing. You could use two parents only produce one child and grab another two parents, but people usually go ahead and do the opposite with the other. I mean, do the same thing with the other parent, just like you did with the bit string. Okay, so the idea here is to specifically work hard to maintain edges which are in the two parents as much as possible. I.e., you know, you imagine you're doing a traveling salesman tour. You know, if you took an edge, it's not just the order that matters. You figure the individual edges are specifically good. So you want to maintain as many edges as you can while still after this exchange of material. So we're really focused on maintaining edges. Okay. Okay, so so what you do, and it doesn't look so much like the other crossovers, you build a table containing the edges from both parents. And the way you do it is so you have the 9 cities. Actually, maybe I should write this out so you can't see what's going on there since the notes are blocked out. So we have one which is easy. We have 1, 2, 3, 4, 5, 6, 7, 8, 9, and the other parent is 9, 3, 7, 8, 2, 6, 5, 1, 4, 8, 2, 6, 5, 1, 4. Hopefully I haven't managed to make any reversals. Okay. Okay, so you kind of imagine we're building a list with all the adjacencies. So for instance, one is adjacent to 2, the first parent, and it's also adjacent to 9. Okay. In the second parent, 1 is adjacent to 5, and 1 is adjacent to 4. Okay. So each of these lists has up to 4 elements in it. So they come from 2 parents, and so similar story for element 2. Similar story for element 3. 5, we only have 2 things because if we look, 5 is adjacent to 6 in one parent, and it's also adjacent in the other parent, and then it's adjacent in 1 and 4. And so if both parents have it, the idea is, well, that's probably a particularly important edge, and we're going to want to particularly work hard to preserve that edge. Okay? So we go ahead and we build this edge table for both parents. Okay, let's see if we can do it pictorially, and as necessary, I'll need to refer to the instructions. Okay. So the first thing we do is we select an element at random. So in this example exercise could potentially be any one of these. We choose one at random. Okay. And so now if we look at element 1 here, we're then going to choose, we're trying to maintain edges as much as possible. We're going to then choose an edge which is, well, first thing we do, once we've chosen one, that means we'll never choose one again. So that means in all these other ones, we can eliminate one. Okay. So our first priority is to choose an element then if it's a duplicate edge, because if they're a duplicate edge, we believe it's particularly significant and we want to definitely keep duplicate edges. There's not a duplicate edge, okay? Our second priority, because it makes sense if we're trying to keep the most possible edges in our list, is to then choose the remaining element which has the shortest list. It turns out between 2, 5, 4, and 9, 2 has a list of 3, 4 has a list of 3, but 5 only has a list of 2. That's if we can't find the common edge, we'll choose the shortest list. So we now choose 5, and 5 becomes our next entry. So we're now at 1, 5, and I can eliminate 5 from everybody. Okay. Now we look at list 5, and our highest priority is to maintain edges which are in both parents, because we assume that's the most significant. 6 is one of these edges which is in both parents, so we then go to 6. So we now have 6, and we eliminate 6 from this. We're at this step, and we're now in 6. And so our choices when we're in 6 is either 2 or 7. 2 has 2 items in the list, no common edge. 7, have I done something wrong? I'm at 6 now, not at 2. So I'm at 6. If I look at 6, I can either go to 2 or 7. 2 has 3 and 8 in the list. 7 has 3 and 8 in the list. They both have 2 items. I choose one of those at random. So in this case, I flipped my coin and I came up with 2. I'm now here. I eliminate 2, and I can continue, but essentially it follows in the same fashion. The details are given here and in the notes. Okay, is that all? This is all we have to say about doing permutations in the traveling salesman problem. Let's discuss some motivations of reasons why people like genetic algorithms. Why do they work? What's the claims? So what I'm going to focus on is really a presentation of Holland's schema theory. We'll see how far we go today. But the basic idea and what Holland was interested in more generally, Holland being the person who, evolutionary strategies were already around. Holland came up with the idea of a GA. The main feature that he had, which the other systems didn't have, was this crossover operator, and he was particularly interested in the bit string representation, for which he went ahead and proved the schema theorem, which allows us to tell a little story about how genetic algorithms may work. Okay? But the basic idea is that GA is something, is an adaptive system. Holland's book's quite fun to read. It's called, I think, Adaptation in Natural and Artificial Systems. He wasn't, if you read the thing, he wasn't necessarily just interested in optimization. He was more interested in building a system that kind of behaved in an online fashion, in the sense that you weren't optimizing a particular landscape. You made a series of decisions, you had some strategy, and you kept changing your strategy in response to the environment. So you can imagine, you took an action on every trial. Your action was determined by your genome, and you got some reward. But GAs tend to be used more for optimization. So the idea, in some sort of adaptive system, you want to explore versus exploit. We'll come to this in a moment. So one is this idea that GAs explore versus exploit, and Holland wanted to make the claim, and maybe in some particular scenarios you can prove that they do some exploration versus exploitation optimally, but in general you can't prove anything about that they explore or exploit optimally. The other solution, given why GAs are useful compared to other optimization, is, in addition to this exploration and exploitation, is this idea of combining partial solutions. That crossover is useful because it combines partial solutions. If I have a good tour here and a good tour there, we can build a new good tour. This is extremely controversial. There's probably well over 1,000 papers which will take various positions on whether crossover is useful or not, or does what it claims of combining solutions as if they're building blocks. It's a well-studied question, for which we still know very little about. This is kind of a complex thing. It's clear on some simple problems you can prove that crossover does what it complains. This building block hypothesis, i.e. it's like the Coca-Cola and the square wheels. Maybe you can get your car with the round wheels and the gasoline by combining two different building blocks, this combination of partial solutions. And so the idea of the schema theorem, which we're going to do, is to kind of tell a story how it's possible that a GA might combine partial solutions. But it's not clear on real data in many setups that that's what it actually does, and that there's other explanations which have been given why crossover would be good, which I will ask about. Okay. The idea of GA is that we should explore versus exploit. What do we mean by explore versus exploit? Well, if you have a complicated search space where there's some smoothness properties, but it's very multimodal, somehow we don't want to only search around one point, because then we will possibly miss other good points. So we want to search different places. But likewise, if we have a solution in one place, we do want to search a little bit locally because we believe things are roughly smooth, and so, if we're at some point on a smooth surface, we want to improve our solution on the assumption that maybe we can climb a little bit near bias. So, in a prototypical algorithm, exploration, you get a whole lot of exploration by random search, but no exploitation. Exploitation, you want to take advantage of your local information. Well, in the discrete setup, you look at maybe just, instead of mutating, you maybe look at each bit position on your GA, and you say, well, I could flip this bit, or I could swap any one of these n squared pairs of cities, and I simply choose the one that maximizes my objective. Or if I'm on a smooth surface, I could somehow go in a gradient type direction to find my objective. So in a GA, exploration in some senses is powered by mutation and crossover, where the distinction isn't perfect here, but they're moving our solution in the space a little bit. Mutation isn't guaranteed to move our solution up or down, but it will only kind of look locally. Crossover, possibly takes bigger jumps. Exploitation happens through the selection function. We tend to, by selecting things with higher fitness, with more likelihood, we tend to end up doing our local exploration near them more by. So we balance the amount that we exploit through selection. Holland gives an argument that he wants to talk about. The claim is that in some sense the way GAs explore and exploit, they do it well in some sense. So he's going to give us one theorem, the schema theorem, and then he's going to give an analogy to another problem where it's kind of clear what a good strategy is. It's a little bit of maths. What would be the optimal way to explore versus exploit? And then we're going to see that a GA explores and exploits in the same way, and whether it's optimal in this one scenario, is it also optimal in this other scenario? Well, maybe not. It's going to depend on the scenario. What's the basic explore, exploit metaphor that Holland wants to bring out? This is the Bandit Problem. There's a lot of research in our department about the Bandit Problem. The model is the following model. Okay, imagine that we're in a happy world and there's these slot machines. Unlike normal slot machines, maybe we're going to assume that these are ones that the likelihood is that you're going to win. Okay, you're looking forward to gambling your money, but you only get to be in happy world a little while. You're given some set of coins, okay, and with these set of coins, your payoff's going to correspond to some for instance, well, in the story that Holland tells, some Gaussian distribution in one dimension with positive means. It doesn't have to be positive, but we're pretending they're positive because we want them to be happy since it's Friday. And some different variances. Okay? So you have these n coins, you have these two slot machines. You can either play this slot machine or you can either play that slot machine. The means and the variances are unknown to you. Okay? You want to make as much money as possible. So the question is, well, how should you play your coins between the different machines? to maximize your expected payback if you want to, assuming expected payback is a good thing. And we're out of time, but just to think this is a very common problem that people want to solve. Let me give another analog one, which I'm interested in. For instance, is online advertising. You go to you're an advertiser, you want to display an ad on a website, you'll make more money if a user clicks through on an ad. But the question is you don't really know which ad is popular to display. If you only show one ad, you only get feedback on that ad, and so you won't get a good idea if the other ad is good to display. But if you show both ads equally and one ad is not so good, you're not maximizing your payback. So how do you explore and exploit? This is a common bandit problem, comes up in many scenarios. It's a classic online machine learning problem. And have a good weekend. But if you have any final questions, please ask them now. Otherwise, send me email or hold them until next week. Okay, thank you.
Is the thing you were just talking about online advertising?
What?
The thing you were just saying about online advertising, is that actually a formal area of research that people have worked on in the department, or because my background is in online advertising, I work for eBay and Tesco.
Yes. There's a, I believe